Hello, Mr. Aaron, Mr. Ryan. Yeah?
Hello.
Oh, how are you today?
Good.
Good? So remember a few months ago we talked about, I talked about this number of perfect squares. For example, 12. If you want to represent 12 in the sum of perfect squares, what would you represent? It equals 4 plus 4 plus 4, right? Because this is the perfect square, yeah? And 13 equals what? 13 equals what? Can you represent?
4. No, wait.
Yeah, keep going, yeah, you're right, yeah. 4.
How? 4.
4 plus what?
9.
Yeah, look, a perfect square. Yeah?
Perfect square.
These are
We
perfect
don't need
square.
this.
Yeah, I know, perfect square. So these needs 2. These needs 3 number. Yeah? Got it?
The least.
Least, yeah, of course. If you know the least, what would that
If
be?
it's a square number, it's definitely 1.
Yeah. Like if you want to the most, right? Then 13 would be 1 plus 1 plus 1, yeah? That was 13 because 1 is the perfect number, yeah? Perfect square number. So our task is given a number like 13, you need to tell me that you need 2, right? And if it's 12, you need to tell me 3.
For me, you need 2.
Right? 8.
4. Yeah.
Yeah. For 6, what's 6?
Later, I will be
6.
1.
6.
6. 4, 1, 1.
Well done, 4, 1, 1. Yes. And how about 7?
3, 3.
4 plus
2.
no?
2
4
plus 1 plus 2.
No, 2 is not perfect square number.
4 add 1, 1, 1.
So in theory, okay, it's a very complex mathematics theory. In theory, at most 4 numbers. 4 numbers. You cannot find, if you find a 5, then it's not optimum. Okay?
How about 23?
23, okay. So can you find 23? Let's go. 23. 16 plus what?
4. Plus. No, they can't.
Yeah, 4. No?
No. 3.
No, 3 is not perfect square number.
2.
2 is not.
1.
1. But yeah, it's 16. They are 9.
Wait. First, how about 9, 4, 1?
Yeah, perfect. Look at that 4. Yeah, because if you're choosing 16, you can't make it into the 4 numbers. Yeah. Because 16, what's left? 7 left, and then we know 7 is 4 plus 1 plus 1. Yeah. So that's 5. But you can actually find 4. Okay. So this is the example of. This is the example of the greedy doesn't work. You know the greedy? Well done. This is a perfect example. If you 23, what's the largest perfect square number that is less than 23? 16. Yeah. But if you pick 16, you can't finish it in 4 numbers. You see? So this is the perfect scenario that the greedy doesn't work. The greedy. You know what's greedy? Yeah, greedy.
Hungry.
Yeah, picking.
Hungry.
Yeah, 23. I pick the largest number, perfect square number that is less than 23, which is 16. But if I pick a 16, I make the wrong choice because if I pick 16, I can't finish using less or equal 4 numbers. I have to pick something different, which is 9, and 9, 4, 1. Well done. Okay, so any idea how we are solving this problem? How are we solving this problem? Remember dynamic programming. What's dynamic programming? Remembering. How are we remembering? Look, if we pick 16, yeah? And what's left?
7.
But we already know the 7, yeah? Yeah, we already know that 7 needs the 4 numbers. Yeah, so we don't need to calculate 7 again. So if we can find some way to memorizing this thing, and then we can reuse it. So basically, if we use the function fn to represent the number of the perfect squares that can be summed up to n, yeah? So fn equals to mean fn, and we are choosing the minimum, yeah? Choosing what? So Fn minus j times j, yeah?
Yeah.
Plus 1, right? And this j, this needs to be bigger than 0, right? Alright? So look, if we can find a way to iterate all the numbers and then we can update these. Right? Do you get it, Eric? Look, j, we just need to iterate j between what? Between 1 to square root of n, right? Yeah? Now we need to find out this fn. Look, this is fn, this is a subproblem, a smaller problem. Yeah? Look, if this is 23, yeah? Look, fn 23. And then, if j equals 3, 4, right? 4, then j equals 4, then 4 times 4 is 16, right? 23 minus 16 is 7, yeah? So basically, f23 equals mean, this is just an example, f23, we keep updating the f23 with the smaller number, f what? f23 minus 4 times 4, right? This is f7, right? Yes?
Yeah.
And need to plus 1, right? Do you know why we need to plus 1 here?
No.
Look, f7, let's say f7, we know 4 numbers, yeah? Right? f7, we know 4 numbers. 4 numbers, yes? Am I right? And then 7 plus 4 times 4 equals 23, yeah? f7 is 4 numbers. 4 numbers plus a perfect square number equals 23. So the 23 is the 4 numbers plus 1 number. Alright? Yeah, do you get it? Here. Okay, so look, 23 minus 4 times 4. This is the perfect square, 16 we are talking about. Right? And we know this is f7, this is 4 numbers. And now we are deducting perfect square, which is 16 here. So it means that we have one more extra number to add, right? To update. Am I right? Okay?
Yeah.
So if we check all the possibilities between I and square number of n, then we find the answer. Am I right?
Yeah.
Okay, so let's write it. And how many dynamic programming are we talking about? Do you know? How many kinds of dynamic programming? How many kinds of dynamic programming?
Memorization.
And what's this? Memorization, what's that?
Remembering.
Memorization, recursion with the memorization. What do you call it? Is it
Top down, bottom up.
yeah, is it a top down or bottom up?
Top down.
Top down, yeah. Memorization with recursion is top down because if we want to calculate fn, yeah, we are solving it into a smaller problem, right? And we remember it, yeah? Like a Fibonacci number. If we want to calculate fn, we need to calculate fn minus 1 and fn minus 2, right? Remember the number of the derangement, remember? Derangement, yeah? Is 2 1 a derangement? Yeah, derangement permutation, yeah? Yeah. So look, Fibonacci number fn equals fn minus 1 plus fn minus 2, right? Yeah? So derangement, you just times n minus 1. Yeah, remember? Do you still remember here? This one, yeah? Yeah? It's the same. So top down is that I want to calculate fn. And I need to solve a smaller problem first. Yeah? But when I calculate fn, I may have to solve the smaller problems multiple times. And in order to speed it up, we need to add what? Add what? The magic keyword above the function, what's that?
Cache.
Cache, yes, well done. To memorize it, let's make it top-down dynamic programming. Am I right? Okay, so let's do this. Fn is represent the number of the least number of perfect squares to add up to n, right? Yeah.
It's
So
been already 9 minutes.
yes, that's fine. Okay. Define Fn. What's missing?
Column.
Column,
Oh,
okay.
and also cache.
Yeah, cache. I'll remind you later. Okay. If n equals 0, f0, how many non-perfect square numbers add up to 0? 0. 0. We make it a 0, perfect case, yeah? 0. Yes?
0.
Okay, so the answer equals a very big number at the beginning. In Python, we can use this a very big number, floating number, and convert it a string, INF. What's INF stand for? A very big number. What's this stand for? Yes, we're done. Infinity. Infinity and beyond, yeah? Infinity, floating. So infinity, a string, converting to a float number. So it means a very, very big number. Yeah? Okay. Yeah. So look.
Tilted 8.
Oh, yeah, infinite. So basically it's 8. You're writing the sideways, yeah? Yeah, so this is infinity, and if you put the minus, it means the negative infinity, yeah? So look, this is a line, yeah? This is 0 here. And you going that way, infinity. Going that way, negative infinity, yeah? Got it? So it's a symmetric line, right? Got it? So look, answer is that. Then we have to do this I equals 1, okay? So while I times I smaller equals n, right? Ready?
Yeah.
Why I times I smaller, then I will do this answer equals mean. Look, we are getting the mean. Answer and what? F n minus, look, tell me what to do. I times I. What's missing here?
Minus, add 1.
Add 1, yes, you remember that, add 1. And then return what?
Return answer. Yeah!
Return answer.
And cash!
Wow, you know I'm talking about, yes, cash.
I said it 2 times.
Cash. So this is eventually making it what? Dynamic programming, yeah. But there's something missing here. That's something missing here.
Kalim.
That's something.
Cash.
No, because I will be needed to increment 1. So let's missing I equals 1. So because we tried 1 times 1 is a perfect square. Is 1. 1 is 2, yeah. Look, 1 is 2. 1 is 2. 2 times 2 is 4, right? Yeah. Fn minus 2 plus 1. When I is 3. 3 times 3, 9. N minus 9 plus 1, right? Yeah. So basically, Fn equals Fn minus 1 plus 1, and Fn minus 4 plus 1, Fn minus 9 plus 1, and Fn minus what plus 1? What's next? What's next? When I is 4.
F.
N minus 4 times 4, 16 plus 1. And what's next?
5.
25 plus 1. Yeah, you see? So all this possibility I need to consider, and then I will get this minimum. Yeah? Yeah, getting the minimum. Okay, so this is the top-down dynamic programming. What's the complexity? Is it easy to see? Is it easy to see? What's the time complexity? Can you make a guess?
I get ON.
O-N, no.
It doesn't.
No, because look, here is what? Is O square n, right? Square n, right? And then you're needing to calculate n, so it's O(n) square n.
ON.
Square n, yeah. Maybe it's not easy to see, but let's turn this into bottom-up dynamic programming.
You still need a cache.
No, from the bottom up we don't need. Look, remember this cache we can edit the parameter like a notebook, yeah?
Yeah.
And then we can if the end in notebook and we return notebook end, and before this we return answer. We set the answer not to notebook end and return answer, yeah?
Yeah.
Okay. So look. So for the bottom arm we need an array. Let's say dp equals. Let's make everything bigger, infinite, yeah? Infinite and times n plus 1, okay? Because from 0 to n, yeah? From 0 to n there are n plus 1 elements, am I right? Yeah? Yeah? Am I right? Okay, so now dp0 is 0, okay? This is easy, yeah? And then for I in range,
Yeah.
1 to n plus 1, right? Here. And then here, look, j equals 1. Y, j times j, you tell me, okay? Smaller equals I. Yes, look. And then what should we do? dp, alright? dpi equals mean dpi, and then dpi minus j times j, and what's missing here? Look.
Cash. Column.
No.
Column.
I from 1 to n, and then j times j is
Add 1.
yeah, add 1, yeah, it's the same thing, yeah, remember? Yeah, and then j what? J what? 1.
J
Add 1, yeah, j add 1, because j from 1, and then the next one is 2 times 2, and next one is 3 times 3, yeah? I minus 3 times 3, yeah, you see?
Yeah.
Okay, and return, what, we have an array, and what should we return? Return here. What should we return? dp. dpi is means the number of the least number perfect squares to represent. So dp what? dp what?
DPI.
I, what's I? No, I is not. What we are looking for
Dynamic
n.
programming.
dpn or dp minus 1 because it's the last number, yeah? Yeah? dpn or dpi, okay? So you see, look, this is n, yeah? On, yeah? And look, this one. O square n, yeah? So you times it together. What's this? N square n, yeah? Got it?
Yeah.
Look, this is the bottom up because we are calculating from, look, we are calculating dp1. dp1, look, this is range from 1, yeah? Look, Eric. And then dp2. We are calculating dp from I, 1, dp2, dp3, dp4, yeah? dp5. We are calculating bottom up, right? Ryan, we are calculating bottom up. Do you get it? Yeah? This is bottom up, yeah? And the other one is top down, right?
Yeah.
Dynamic programming, okay? Okay, so let's another quiz, which is 15. How do you represent 15 using these square numbers? These perfect square numbers. 15, come on. 15.
15. Square number.
9.
411.
4.
Wait.
No. 9411 is 15, yeah? Can you better? Do it better?
914.
No, 2 is not perfect square.
951.
5 is not perfect square number.
A square.
Perfect square number. Is there any other
What's
choice?
the perfect square number?
2 plus
Well, the square number. Not.
2 is not, right?
2 is not.
4 plus 4 plus.
Or you could use it 9, 4 and 1s.
Yeah, I think this is ideal. Yeah.
See, I told you.
Okay,
4
okay.
and
Okay.
4.
Okay, so that's it for today.
Bye.
Bye bye.
Bye.
Bye.